Hello everyone. My name is Songap Im from Department of Chemical and Biomolecular Engineering at KAIST. And today I'm going to present my work of vapor phase deposited functional polymer films for electronic device applications. My presentation is about introducing a new kinds of the vapor phase deposition process to deposit high quality of the functional polymer films and so their device applications. So I hope you find the process is pretty interesting and useful. And so I want to give you some kind of idea of how this kind of thing can be applied for the electronic device applications. The process that we use is the iCVD process. So the CVD process, I believe you should be pretty familiar with that. But for someone who are not familiar with that, I would like to explain briefly about that. So CVD stands for the chemical vapor deposition. So chemical means there's a reaction. And V means in the vapor phase, and D stands for the deposition. So some reaction happens in vapor phase, and the final product is the films. So like that kind of thing is all we can say chemical vapor deposition. So in this process of the iCVD process, the I stands for the name of the chemical reaction, which is initiation reaction. So in this process, a initiation reaction triggers the polymerization reaction. And with this process, we can deposit various kinds of the functional polymer films. So the uh, basic mechanism of the CVD process is like that. So, so this is the reaction scheme of the CVD process, where the initiator decomposes to form the radicals, and these radicals are transferred to the monomer to form the monomer radicals, and the recombination of these excuse me, recombination of these radicals increase the molecular weight that forms the polymer films. And actually, this process is very, very well known, free radical polymerization, and that has been known about 80 years ago. And there's about 5 Nobel laureate has been awarded by this reaction. So it is very well established. And actually, the iCVD process is kind of the vapor phase version of this very well-established free radical polymerization. Briefly, so the reaction chamber looks like this, and this is schematic figures. So we flow the initiator and the monomer. So the initiator flows in, and the monomers is like this kind of hexagon. And so the material of the initiator that we use is peroxide materials, which has very weak oxygen bond that is readily decomposed with the temperature higher than 150 degrees C. And on the other hand, this hexagon is monomer, basically the organic chemicals, which is the typical decomposition temperature is around 350 degrees C or higher. So one thing decompose at around 150 degrees C, and the other thing decompose higher than 350 degrees C. So if we supply a heat like this hot filament here, if that is the temperature is somewhere between that, say that 200 degrees C to 250 degrees C, then the initiator can be decomposed very selectively, while this functionality of the monomer will be fully retained. So when these two chemicals flow into the system, they hang around, and this initiator will decompose to form these radicals, while this hexagonal monomer will hang around, and that will just absorb on the cooled substrate, and these radicals are transferred to this monomer, and this monomer recombine together to form the polymer, and the polymer film will grow from the cooled stage and grows up from the substrate. That is basically what happens. So actually this movie can explain a little bit more. This is actually the system of that what we use. So in here, this black initiator and blue monomer flows in, and with the heated filament, this black initiator forms the red radicals, and that recombines with the blue monomer to form the polymer that grows up from the polymer film. So this is one very simple process that, as you can see, with the empty chamber, we have just the cool stage and the hot filament, and we control the flow rate of the initiator and the monomer and the process pressure and the filament temperature and the substrate temperature. With this control, we can deposit various kinds of the functional polymer films. So why iCVD? So the advantage of iCVD is quite a lot. Let me explain briefly. First of all, the process utilizes only the initiator and the monomer. We don't use any kinds of the solvent. We don't use any kinds of the additives. And all the reaction happens in addition reaction. So addition reaction means there's no byproduct. So even if we do not have post-cleaning procedure or post-washing out, rinsing step, the polymer itself is very, very clean. We don't need post-cleaning process, no additive, no solvent. And that is critically important for the application to electronic device application, which is majorly governed by the level of the impurities and the biomedical applications, where like this kind of byproduct may be very toxic for the tissue or any bioorganism. And secondly, the process temperature of the substrate is near room temperature. It is around 10 degrees C to up to 40 or 50 degrees C, and we don't use solvent. So we can use any kinds of substrate that we need. So like not just the silicon wafer or the glass substrate, we can use fabric, we can use paper, we can use membrane or any kinds of flexible substrate or rubber substrate as we want. We do not damage the surface. And third thing is, important thing is the conformal coverage. Since the polymer film grows from the adsorbed monomer and it grows from its surface, it gives pretty good conformal coverage characteristics, which critically differentiate this process from liquid phase one. If we think it is liquid phase process, and the solution will be filled between this trench because of the capillary force, and there will be no coating at its side wall, right? So the design will be changed and coating will not be uniform, but with these conformal coverage characteristics, we can give very good conformal coverage characteristics. Actually, so this conformal coverage characteristics can be applied various kinds of things. This is one very high aspect ratio trench structures of the height of the 10 micron and width is about 1 micron, like that kind of thing. This is multiple carbon tube is modified with, as you can see, like this, like 5 nanometer thick iCVD polymer coatings. This is highly porous membrane separator for lithium-ion batteries, and this porous structure will be fully retained. And so the process is the vapor phase process where mixing is always favorable. So the story is simple. So oil and water in liquid phase process, some kinds of combination may form phase separation. But on the other hand, in case of the liquid phase process, in case of the vapor phase process, oil vapor and water vapor is fully miscible in vapor phase because of the huge gain of the entropy. So we can mix anything that we want. So for example, if the one thing has very hydrophobic with the contact angle of 100 degree, and the other is fully hydrophilic and that is readily wet with the water, the contact angle will be 0. And with this kind of combination, we can freely mix it together, which is very challenging in liquid phase process. And we can control the composition. For example, if we want to make hydrophobic one, so contact angle will be, say, 80 degree, then we can flow more amount of the hydrophobic one and less amount of the hydrophilic one. Like this way, we can precisely control the composition of the component by copolymerization of the monomers, and we don't need to think about the composition of the monomer, its characteristics. So we can generate various kinds of compositional variation in the polymer coating. And we can also stack the polymer film. We can cross-link the polymer film. So during the process, we can add cross-linker, and so we can add a film as much as we want. And very conformal way, we can stack the film. And finally, the process does not require any kinds of the pre-treatment because the polymerization occurs by the adsorbed monomer, and the adsorption can be governed by the temperature. If the temperature is pretty low, then the monomer will be adsorbed. So basically, when you do some kind of spin coating, you normally use some kind of plasma treatment for the spin coating. But in this kind of process, we don't need any kind of the pre-treatment. So that's one very important advantage of this process. Most of all, so the iCVD can synthesize various kinds of the polymeric films, like these kinds of the epoxy polymer, polymeric acid, or polymeric base, or fluoroalkyl polymers, which is very hydrophobic, cationic polymers, hydrogel polymers, or organosilicon polymers, and so forth. So we have more than 60 different kinds of the polymer can be synthesized by the iCVD process. And the combination of this, so epoxy coupled with the hydrogel or the acid material with the hydrophobic one, like this kind of combination is freely available, which makes the composition of the uh, polymer synthesized from the iCVD practically numerous. So with these kinds of the advantageous characteristics of the iCVD polymer, in our lab do a lot of research, including flexible electronic devices and the biomedical applications, and some kind of nano-adhesive or microfluidic applications, and general surface modifications. And we have many publications in this area.